Hello everyone, welcome you all to this presentation. So in this video we will see about how we can convert the context-free grammar into pushdown automata. So you know what is context-free grammar as well as pushdown automata, right? So the context-free grammar is a formal grammar for representing the set of strings accepted by the formal language, okay? And pushdown automata is a automata. It is used for recognizing the context-free grammar, okay? So in this video we will see how we can convert the context-free grammar into pushdown automata. Next we see the contents of this presentation. First we see the introduction, then context-free grammar, then pushdown automata, and conversion of context-free grammar into pushdown automata, and the summary. Next we see the introduction. Before learning how to convert the context-free grammar into pushdown automata, we should understand what is the definition of context-free grammar as well as the pushdown automata. So here the CFG stands for context-free grammar and PDA stands for pushdown automata. Next we see the definition of context-free grammar, okay? So how we can define the context-free grammar formally, okay? So the context-free grammar G can be defined using 4 tuples. For example, G equal to VTPS, where V stands for finite set of variables, T stands for finite set of terminals, and P stands for finite set of production, and S is a start symbol. So V is also called as non-terminals, okay? Variables is also called as non-terminals. T is a terminals, and P is a production or rules, and S is a start symbol. So next we see what is pushdown automata and how we can define the pushdown automata, okay? The pushdown automata is similar to the deterministic init automata for a regular language, okay? So for any regular grammar, we have a equivalent deterministic finite automata. Similarly, for any context-free grammar, we have a equivalent pushdown automata, okay? So we can define pushdown automata. It is used for recognizing the context-free grammar, okay? So there is a difference between the pushdown automata as well as the deterministic finite automata. So here the pushdown automata can use to store unlimited amount of information, whereas the DFA can store only a finite quantity of information. So we can define the pushdown automata as a finite state machine along with the stack, okay? It is a finite state control along with the stack for representing or storing unlimited amount of information, okay? So this is a model of a pushdown automata. So it have a finite state control. So along with the input tape, we have one more input, that is stack input, okay? So for any transition, it takes the input from the input tape as well as the stack content and check whether the input string is accepted or rejected by the pushdown automata. So next we see how we can define the pushdown automata. The pushdown automata can be defined using 7 tuples. For example, consider we have the pushdown automata P, and it can be defined using 7 entities: Q, sigma, gamma, del, Q0, Z0, and F, where Q is a finite set of states, sigma is a finite set of symbols, and gamma is a finite set of stack symbol, and del is a transition, Q0 is the initial state, and Z0 is the initial stack content, and F is a set of final states. Next we see the conversion of context-free grammar into pushdown automata, okay? So we will see what are the steps necessary for converting the context-free grammar into pushdown automata. So there are 4 steps that are required for converting the context-free grammar into pushdown automata, okay? So we will have the grammar. So from the grammar, we are going to convert the pushdown automata. First of all, we have to consider one state, okay? Here you assume the state Q. So that is the state present in the pushdown automata. And the second step, the start symbol of the context-free grammar is considered as the initial symbol of the pushdown automata, okay? So every grammar we have a start symbol, okay? So that will be considered as the initial stack symbol of a pushdown automata, okay? So next you write the transition rules, okay? For every non-terminal as well as terminals, we have to write the transition rules, okay? So for example, we have a non-terminal A and have the production A tends to alpha, okay? And equivalent production rule is, transition rule is del of q comma epsilon comma a equal to q comma alpha, where a is a non-terminal, it is present in the left hand side of the projection, and alpha is a set of terminals or non-terminals, it is present in the right side of the projection. A tends to alpha. Okay, so next one is how we can write the rules for the terminal symbols. Okay, for every terminal symbol present in the context-free grammar, so we have to write a separate rule. Okay, so for example, consider we have a terminal small a present in the context-free grammar. So equivalent transition rule is del of q comma a equal to q comma epsilon. Okay, so this is for every terminal. Okay, so this is a way we can convert the context-free grammar into pushdown automata. Okay, so next you see the example for converting the context-free grammar into pushdown automata. Okay, so for example, consider we have a problem. So create a pushdown automata for the provided context-free grammar and check if 0, 1, 0, 0, 0, 0 is accepted by it or not. Okay, so consider the grammar S tends to 0 BB and B tends to 0 S, 1 S and 0. So in this grammar we have two non-terminals, one is S and B, another one is B. Okay, where S is a start symbol. Okay, and we have two terminal symbols, that is 0 and 1. Okay, so next you see how we can write the pushdown automata equivalent to this context-free grammar. Okay, so first we define all the entities of pushdown automata. Okay, so from the context-free grammar you are going to consider pushdown automata. So for example, consider A is a pushdown automata you are going to construct it. Okay, and first you assume the state q. Okay, q is one of the state in the pushdown automata. So next we have to define the symbols. So here the symbols are 0 and 1, and then we have to define the stack symbol. So it includes both terminals as well as the non-terminals. So S comma B and 0 comma 1. Then you define the del function, that is transition function. Then start state, that is q is a start state and S is a initial stack symbol, and next we have a final state. Okay, so next we write the transition rules. Okay, so for each and every terminal as well as the non-terminal we have to write the rules. Okay, so here we have two non-terminals S and B. So the correspondingly R1 and R2, it is for two non-terminals. These are the two rules for the non-terminals. First you write the rule for the non-terminal S, that is del of q comma epsilon comma S equal to q comma 0 BB. Okay, and second one is for the non-terminal B. So we have three alternate projections, so we have to write like this. Okay, q comma 0 S, then q comma 1 S, then q comma 0. Then here we have two terminals 0 and 1. For each terminal you have to write the projection rules. Okay, that is del of q comma 1 equal to q comma epsilon and del of q comma 0 equal to q comma epsilon. Okay, so the construction is over. We are converting the context-free grammar into pushdown automata. Okay, so these are the entities of the pushdown automata. So next you see whether this string is accepted or not using this projection rules. Okay, so next we see how we can process the input string using pushdown automata. Okay, so here you consider the string 0 1 0 0 0 0 and use the previous PDA construction example and you check whether the string is accepted or rejected. Okay, so for that what you do is you have to use the instantaneous description of pushdown automata. So the idea of pushdown automata consists of three entities. So first one is a state, then we have a input string, then we have a input stack. Okay, initial stack. Okay, initial stack content. Okay, these are the three entities. Okay, and then you use the tangential notation for representing the move. Okay, so first case. Okay, so the current input symbol is 0 and in the initial stack content is S. Okay, so here S is a non-terminal, so you have to replace this non-terminal by its projection. So by applying the rule R1. Okay, so S is replaced by 0 BB. Okay, Now we check, okay. So the input symbol is 0 and the current input stack symbol is 0, okay. So both are matched. So what you do is you have to pop the symbol from the stack, okay. So the remaining input is 1 0 0 0 0 and the top of the stack we have the symbol B. So B is replaced by its production. So apply the production 1 yes, okay, based on the rule R2, okay. And then so now in the top of the stack the symbol is 1. Similar way the current input symbol is 1. Both are matched. So you have to pop the symbol using the production rule R3. Okay. And then in the top of the stack we have the symbol yes. This is a non-terminal. So you have to replace by its production. So 0 BB. Okay. Again there is a match, that is 0 and 0. Okay. Both symbols are matched. So you have to pop the symbol from the stack using the production R3. Okay. Then again in the top of the stack we have the symbol, we have the non-terminal B. So we have to replace by the production B tends to 0, that is Q comma 0. Okay, now check the current input symbol as well as the symbol on the top of the stack. So both are matched. So you have to pop the symbols. Okay. Now the remaining input string is 0 0 and the top of the stack we have the symbol B. It is again replaced by 0. Okay, it is based on the rule R2. Now there is a match. You have to pop the symbol 0 from the stack using the production rule R4. And now you have the symbol, okay, 0 on the current input symbol and B is on the top of the stack. So you have to apply the production rule R2 and replace B by 0. Now the current symbol as well as the symbol on the top of the stack is matched. So you have to pop the symbol. Now the stack is empty. So we have to say the current input symbol, that is 0 1 0 0 0 0 is accepted by the given pushdown automata. Okay. So this is a way we can use the instantaneous description of pushdown automata and the tangential notation for recognizing the input string or checking whether the input string is accepted or rejected by the pushdown automata. Okay. So next we see the summary of this presentation. So in this video we have learned a simple technique to convert the context-free grammar into pushdown automata. So also we have solved some examples, okay, that helps you to understand the steps for converting the context-free grammar into pushdown automata. Okay, thank you.